Okay, so I'd like to thank the organizers for the opportunity to talk. A lot of what I'm going to talk about has been done in collaboration over the recent years with Christian Caroli. I'll try to talk a little bit about more recent work which has been done in the PhD of Joydeep Chatterjee. So the idea of the talk is to look at various numerical results which help us understand the elementary mechanisms of deformation, of plastic deformation. And the starting idea is to try to focus on what happens in a zero temperature glass. The idea that as soon as you are at low temperature, the system will essentially vibrate around local inherent states. And so it makes sense to look at the limit where the temperature first is really zero, so that the system will usually lie in one of the local minimum, and then you look at the deformation, and when you apply some deformation on these systems, it will follow adiabatically the external changes. And in these limits, the dissipation occurs because from time to time you will push the system by some instability threshold, and then it will need to relax in search of a new local minima. So a way to implement that numerically is simply to minimize energy and to apply extremely small amounts of strain. And if you look now at some, for example, the stress versus strain rate, this gives some kind of serrations, which here just show that here you just the branches which corresponds to the loading of these local minima, and sharp drops which corresponds to the dissipative events. Just 2 points that in all what I'm going to talk about, we focus on the steady state because it's a very well characterized state where we do not care about exactly about the preparation of the sample. The system reaches a critical state. And it's, of course, of direct relevance for soft glasses, maybe a bit less for metallic glasses, where often you focus on transients. But it's, I think, a way to really understand what happens, how plasticity works. Another thing is that I often show numerical results which involve these Lee-Edwards boundary condition. I think everybody here knows about that. So a few lessons from AQS simulation. The first thing that we learn in AQS simulation is that if you look at these drops in fact are very complex events which spread over the whole simulation cell. And they are complex events, but if now you look, for example, at the onset of these events, you see these quadrupolar patterns which are the trace of shear transformation zone. And so the picture which comes from the AQS simulation that plastic events are avalanches of elementary flips. If they are avalanches, it means that you expect some form of scalings of the energy drops, and in fact there are a variety of works to attempt to measure the scaling of energy of, for example, energy or stress drops. And they show some scaling with system size which are essentially tell you that you indeed have a non-locality of the dissipative events. And what's really important about this scaling, I mean, there is, Mark raised a lot of questions yesterday about the details of the distribution of the energy drops. What's really important is that they mean that these flips talk to one another. I think that's what the question which was raised yesterday by Krish. Sorry? These here are just minimization. We'll come back to this. We'll come back to other forms of simulations. Another thing we learned from AQS simulation is that when you go, if you now zoom at just the onset of an event, at the onset of an event, you see here, you see the stress shows a normal form which has a square root singularity. And this is just controlled by saddle node bifurcation because one soft mode is going so zero. So what happens is that you have one local region which becomes soft and then triggers a whole avalanche. If you focus on this soft mode and you analyze it in detail, you find the decay that you expect in the SLB solution. And you can also look here at just individual events as was done by Barra's group. And you find here that, again, you have the right symmetry of the stress tensor, which in fact tell you that these events indeed are local SLB transformation, which means that indeed they modify the stress field at long range, and that's why they can talk to one another. In fact, you can even go a bit further. You can here look at the non-affine field, so that's a measure of softness. Here you have a soft zone here, which will actually here undergo some transformation, and after this zone flips, it will modify here. It will actually here you had another soft zone that you could see, and this guy now will be loaded by the effect of the former one. So these zones actually interact, and this gives rise to a phenomenology in which we see that shear zones are actually very progressively convected towards threshold, so that when you shear the system, you populate the very near threshold region of your zones, and that's why you can have this avalanche type of behavior. The question I'm really interested in is to understand what will remain of this phenomenology at a finite strain rate. And I'll first take a very small step by looking at the situation when still the temperature is still zero. But now in order to apply, so I'm now going to strain my system at a finite rate, and to do that I need to introduce some dissipative forces. I do that in a way which is exactly similar to what Mark Robbins was talking about yesterday. And if you have here this difference of velocity, it guarantees that the dissipation is correct in the sense that you do not damp the long wavelengths. You allow them to propagate, but you damp the short wavelength. And in fact, here there is a damping parameter which essentially sets the scale at which you damp the sound waves. And here we choose this scale to be of order of a few particles, which means it's of order of a zone size. Yes.
You cut that off.
At distance 2, which is the distance of the interaction potential. At the cutoff of the interaction potential, of the Lennard-Jones potential. So now just let's look at here the velocity field. So here we look at the velocity. We just shear a system at a very small strain rate. And we look at the velocity field subtracted from the mean flow. So it's the non-defined part of the velocity field. And what do we see? Well, we see exactly what we learned from AQS simulation. We see flips, which have a quadruple shape. We see that these flips actually emit sound waves. So these are only arrows. And when you see this kind of shaded area, it's simply because you have an elastic wave which is propagating through the medium. We can actually look at the speed of the propagation, and it is the shear wave speed. So we have flips which emit acoustic signals which are transported throughout the medium at the shear wave speed. Okay, so all the ingredients that we learned in AQS simulation will lead to avalanches are still there. And the question now is whether we continue to have actually avalanche behavior even at finite strain rate.
Do you see no compressive waves at all?
Sorry?
Do you see no compression waves at all?
Little, no, not much.
So there are some.
There must be some, but the compression modulus is large, so it's almost incompressible. So in order to characterize now the correlation, the problem is that if we just look at the movie I just showed, we cannot characterize very well the correlation between these events. Another thing we can do now to characterize that is just look at how strain accumulates inside the system. So that's the same system I showed you before, and here that's for macroscopic strain of 1, 5, and 10%. Here are maps of the local strain, and what you see that the local strain accumulates in a very non-homogeneous manner, and also in a manner which is extremely, what you see here is that you have a lot of directionality. And this directionality must come from the fact that you have directional interaction, which is exactly what HLB tells you. Okay, that's just a picture, and the problem now is that we want to be quantitative. In AQS simulation, we could be quantitative because by looking at stress drops. And the problem is that as soon as you introduce the finite duration in the system, you no longer have very sharp drops, simply because you have a finite duration of your dissipative events. And the problem is that the type of analysis which involve looking at stress drop are not very robust. They are sensitive to a lot of details of your dynamics, and we need to find better observables than what were used in AQS simulations. So I'm back to AQS just to bring up another observable, which is in fact particularly interesting. So here that's one AQS result, where here you have against this shear cell. The y direction is the direction which is transverse to the flow, and what we look here, we look at the delta y square, the diffusion of particle in the transverse direction. And this is plotted divided by strain. There is no time in this system. The only measure which is analogous to time is strain. And if we look here at the delta y square divided by strain, we find that it reaches for it reaches a plateau value at larger strains, which tell you that the particles reach some kind of diffusive behavior. What's very surprising here is that this plateau value, which you would call a diffusion constant, varies very significantly with system size. And that means that, again, these displacement fields are extremely non-local. They sense the boundaries of your system. That actually may look odd because you would like to think of a diffusion constant as something which is actually a constant, a material constant. But okay, that's an effect. Here we can actually capture an effect of the elastic interaction, and we will go in more detail about that. Now, if we go at finite strain rates, and we do exactly the same thing, and we look again for different system sizes, we have exactly a similar result with diffusion which reaches a plateau, but a plateau, here we are in 2 dimensions, and we'll see that some effects are 2-dimensional and some are due to the elastic correlations. And here this plateau increases very significantly with system size. So what we do then, we collect all the values of these plateaus, and now we just plot them. Here we plot the values of the plateau, of the diffusion constants, at different strain rates. So each of these curves corresponds to one strain rate, and here you have these diffusive values as a function of the system size. So what do you see? You see here the higher part of the curve corresponds to the lowest possible strain rates in your system. And so when you strain the system extremely slowly, you reach a regime where your diffusion constant grows almost linearly with system size. Now, if you shear faster, you will lose this effect of correlations, and you will reach here a regime where the diffusion constant now behaves like a log of the system size. So what I'll explain you next is why this captures information about the correlation between flip events. So, yes?
What spatial dimension?
This is the side. It's a square box L by L.
No, I mean, how many dimensions does your space have?
What do you mean? 2. Yes, it's in 2 dimensions. Yes, exactly. So the log is a 2D effect, but the linear part is not. So first thing, there is one thing which underlies everything I'm going to talk about, is that when we think of the plastic response as a sum of flip, we'll decompose this as a sum of flip. We'll just introduce a typical strain of the SLB flip, a typical size. We're in 2D of the zone where the flip occurs. SLB then tells you that the stress drop, which is due to one of these slips, has the form, it's proportional to a squared delta epsilon 0 divided by L squared in 2D. Now it means that if you look at the long strain interval, the number of flips times the stress released by each flip must just be equal to the whole stress you load on your system. And that just sets a number of flip per unit over an interval delta gamma. And essentially, this tells you that the number of flip is simply proportional to the volume of the system and proportional to the strain. So it's just very, in fact, I'm just saying here that introducing these 2 parameters sets a density of flips per unit volume and per unit strain. Now, as soon as you are working at finite strain rate, this tells you that there is a rate of flips, and the rate of flips has this form. So, now if we assume that these flips are independent, and we look now at diffusion of a particle over a large strain interval, a particle I will receive SLB signal coming from different sources, and if we assume that these SLB signals are independent, now the diffusion, we just take delta y squared, will be the number of signals received times the fluctuation of displacement, which is due to the SLB field. And if you do that, SLB gives us a solution for this. We can calculate from this the fluctuations of displacements due to one flip. We know the number of flip per unit strain, and that gives us an estimate of diffusion, which presents a log L behavior, which is indeed a property of 2D, 2-dimensional elasticity here. So. That's right. Even if it's incompressibility. But okay, we can just let's look at what SLB tells us about that. So now if we look at here, so now we have this expression for the diffusion constant, which has a log behavior. And this log is something that we would expect. We expect the flips to become independent when we strain the system fast enough so that we are away from the quasi-static limit. And what we want to understand is how we increase or lose correlations depending on the strain rate. So here, if we look now, so this expression, we can use this expression of a log. Here we found that at the highest strain rates, we had a log behavior. And from this log behavior, we can extract a value of a squared delta epsilon 0, which actually corresponds to zones which have of order a few particles, and in which you have strains of order a few %. So here we have at very high strain rates, we can recover a very simple image of flips which are decorrelated. The problem, of course, is that when you go to lower strain rates, you will find increasing deviation from this log behavior. And this increasing deviation must tell you that you start to have correlations in your system. So that's the correlations we see. And the problem is to try to capture this, to relate this correlation in the simplest way to the diffusion. And so what we do here, we make a very simple assumption. Our simple assumption is to assume that all these avalanches have a linear extension L, and we introduce a typical length scale, which is a way to introduce a correlation between the HLB sources. As soon as we have this now, we will have a number of avalanches. We had before number of flips. The number of avalanches during the strain interval delta gamma is just the number of flips divided by the flips inside each avalanche. And we just do the same calculation as before. So now we just have a delta y square HLB, but now which comes from correlated sources, and so which gives a different expression. And we just do exactly as before. We look here at particle diffusion. Particle diffusion comes from the accumulation of signals coming from avalanches. And if we assume now that avalanches are independent, we here have a delta y square, which will grow like the number of avalanche signal received times the fluctuations produced by each of them. When we do this, we arrive now at an expression for the diffusion constant, which introduces an L, which is this linear correlation length, and the log of capital L over small l. So now what we have is that we have an expression for the diffusion constant, which here will allow us to match to asymptotic behaviors. If you, at large strain rate, if we imagine that the flips become uncorrelated, so it amounts to saying that the avalanche size becomes just the size of one of these individual events, then we will recover here a diffusion constant which grows like the log of the system size. Now, if you go to a very low strain rate, and you expect that, and as we saw if we recover the quasi-static limit, and we saw that at very low strain rate, in the quasi-static limit, we know that the avalanche size scales like L, then we recover here a diffusion constant which also scales like L, which explains this result here. The whole problem, however, is to try to understand what's in between these two asymptotic regimes. And the problem is that if we want to understand all of these data, we also need to be able to understand how a correlation length between local flip events will depend on the strain rate. So the whole question is to understand how strain rate will reduce, in this case, the amount of correlations. So the idea is to look at the signals which are received by one zone. So here is a zone, and this guy is in a large medium of size L. And in this whole medium, we know that there is a flip rate, which is this. So the zone is constantly receiving elastic signals coming from a lot of plastic activity which is occurring inside this system. Now, I will, for now, arbitrarily select a subregion of a size small l. And just remark that if I do this, now the flip rate of the near field signals, the field signals which come from this region, is just, of course, of this form. And what I want to look at is the condition under which these near field signals are separated in time. The idea is what? The idea is that when a zone receives a signal, when the question is what allows a zone, a flip here, to be correlated to another event. If it is correlated with another event, it means that the signal coming from somewhere else must arrive, shift the stress of this zone, and allow this zone to flip. And so, if you take a small region here of size L, and if you just take, so we are looking for the condition of L such that the signals coming from within these regions are separated in time. And they are separated, we have signals which have some autocorrelation time, which is just time of zone flip, it's just the size of a zone divided by sound speed. And this is just the frequency of these signals, and if this condition holds, then the flips arrive separately in time, which means that the zone actually sees the different signals which carry the directional information. That condition sets a condition on the length of the region L. Now the problem is that this zone is not only seeing signals coming from this region, but it's also seeing signals which come from outside. So from outside, you have a background noise, which is just the rest. I mean, everything which is not the difference between these two rates, that all the other flips, it's essentially the same thing as that. And now, this noise coming from the far field is a very high noise. So it means that on top of these near field signals, the stress in these regions will do some kind of diffusive motion. And the question is whether the signals coming from far away will blur the information coming from a short-range signal. If you blur the information, if you don't see the stress shift, you cannot be correlated. If you see the stress fields, then you will introduce correlations. So under what condition a shift in stress, so a shift in stress here occurs during a time tau, and during this time tau, the stress noise coming from the rest of the system will introduce a fluctuation of stress which has this form. It's just the rate of all these flips times the time tau times the fluctuation of stress which is due to HLB. We go back to HLB, we compute the fluctuation of stress, we arrive at an expression for this stress fluctuation. And now we just require that this stress fluctuation, the square root of this fluctuation, is smaller than the smallest possible amplitude of a signal coming from length L. We want to know under what condition this zone will see a signal coming from the farthest end of this region of size L. It turns out that this condition is identical to this one. Which means what? Which means that we see here that if we just count the signals and signal frequency, we just set a characteristic length scale L, which is set by strain rate. And below this length scale, all the signals which come from closer than this length scale are signals which will look separated in time. So they carry directional information, and they are actually seen by the receiving zone. The signals which comes from far away are just some noise, but they are noise which will not blur these drops, these changes of stress. Which means that it's a noise which will not, so the ansatz is that provided that this zone sees an individual signal, then it's likely to correlate with the source from where this signal was emitted. So that gives us a notion of a length scale, which is a correlation length between flip events. So we have here a diffusion constant that we can relate to length, and we have here a length that we can relate to a strain rate. And the question is whether the two match, is whether that allows us to rationalize these data. And so what we do is that simply if you plug this inside here, you see that now d divided by capital L should be a function of L square root of gamma dot. And in fact, it's a function, if you plug that in here, you see that it's a function which should decay with an exponent -1 at large values of this expression. So we plug that in, we do this plot, and this is what we find. So what we see here is that we find that there is a crossover between two regimes. There is a crossover between a regime here where the avalanche size is set by the strain rate. So you have finite avalanches set by the strain rate, and these avalanches grow when the strain rate becomes smaller and smaller, and at some point L will reach something which is a fraction of the system size, and you have just a very normal crossover behavior. And here you will find that's the diffusion values, the values of our diffusion constant in the AQS simulations. So you reach here a plateau value which will continuously go to the AQS data. So what we find is that at finite strain rate simulation, we have just a very normal crossover behavior and we have, for systems of reasonable size, we have the strain rate sets a correlation length between flip events. So that was in 2D. The argument we use is an argument which is easily extendable in 3D. And you just have something with a power 1/3. If now you get data from reasonable values for an atomic glass, you find here that for gamma dot of order of second -1, you have lengths, the possibility to have correlations between flips by these mechanisms up to lengths which are of order of microns or a few microns.
Would the general rule be that the correlation length goes like shear rate to the 1/8?
Yes. Oh, so just one thing which is more speculative is that here we also measure in this system our stress versus strain rate, and we find something that if we measure stress versus strain rate, we find a very nice square root behavior. It turned out that there is an argument which comes up very often, at least in rheology, and the idea is that here the difference between stress, the true stress and the yield stress is just the modulus times, it's basically dimensional analysis times the strain rate times a duration of the dissipative event. Now, if the dissipative event is an avalanche of size L, and which is governed by the propagation of acoustic signals, so that's the duration of an avalanche, if we plug that in, we do find the square root behavior, but we also find a prefactor which we estimate to be here 13 when our measured value is 4 point something. So we can just get right on an estimate of the actual prefactor of this power law dependent of stress. So I think I don't have much. Okay, so just to conclude on this, just one thing is that in these AQS simulations, there is a phenomenology coming from AQS simulations. And what we see at finite strain rate is that essentially now we have the effect of noise signals will cut off the correlation length, but will determine a length scale which varies like this, and with a very normal crossover behavior. So I'd like to say maybe a few words, very few words, to ask the next question, because the next question, of course, is what happened next at finite temperature. So I'll just say very few words on that. So we just the same type of simulations, same system with velocity rescaling. We measured our TG with standard procedures, and we accumulate tons of data, and it's really a lot. So just to show you a picture, this is the strain maps for different, as we accumulate strains and at different temperatures. And what you see here is that you continue to have, if you take so our TG is 0.27, so 0.2 is perhaps small compared to TG for any person working on a real glass. But at this value, we already find very, very significant patterns. And it's only when we go above, and even in fact above TG, you continue to see some directionality in the pattern we have. And I think I was very interested by a work by Furukawa and Tanaka, and who see also some pattern above the glass transition temperature. I think that might be related. Just one point about that is that now if we measure the stress in this system, and here that's stress versus strain rates for a different, here that's for different temperatures. So I just showed you a stress versus strain rate curve, which was a constant plus square root. the first thing we see here is that as temperature increases, even for small temperature, we see a very sharp drop of the stress, of the flow stress. So that seems to tell you that there is a strong thermal effect. Now, if you plot stress versus temperature, you see here that, okay, there is a very complicated behavior of stress versus temperature, and you see here at low temperature in particular, it's very sharply dropping with temperature. This arose, of course, then we're interested in a paper by Johnson and Samwer, who actually collected a huge amount of data on metallic glasses, and they proposed to write the temperature, the thermal effect of stress to introduce some term which is of the form T to the power 2/3. And the way they argue about that is based on the fact that the system, as you drive these flips towards threshold, you constantly cross saddle node bifurcations. So the way the theoretical argument is done in Johnson Samwer uses a cosine, and so we wanted to make that a little bit more to our taste. And so we just, essentially the idea that we have is the following, that you have this shear transformation zone, and at t equals 0, each of these zones will flip just when they reach a local instability threshold. At finite temperatures, they just can't flip in anticipation. And now if you just write the probability that the zone, so the idea is just to write a Fokker-Planck equation for the probability that the zone is still in its stable location. And when you do this, and okay, you can just essentially, I will not go there, but just show you that we can do the calculations. And we can do the calculation, and you arrive at an expression for provided some. So the important point is that the barrier that you're crossing is actually decaying to 0, and it's decaying in a form which is controlled by a saddle node bifurcation. And what's very important is that the energy barrier goes like gamma c minus gamma 2 power 3/2. And once you plug that in, you have an expression for this probability, and you see that essentially what temperature does is that it will activate flips in anticipation. And the idea we defend is that it actually works like, it actually works like a shift. It's as if temperature defines new instability thresholds, which are shifted, but the whole underlying dynamics is the same, and that allows us to fit our stress data. Okay, so I'll just finish on this. And okay, so essentially, just one word of conclusion is that we think that at low temperature, we continue to see avalanches. We continue to see a lot of the phenomenology that we learned from AQS simulation with a shift which is due to the thermal activation over a decreasing barrier.
Questions or comments? Mark?
In terms of the last part of your talk, you seem to have a power law dependence of stress on strain rate. So presumably, I mean, we've looked a lot at this issue in three-dimensional systems, and there's initially a logarithmic rate dependence, followed perhaps at very high strain rate by something that's more power law,
there are many,
and a very nearly linear drop with temperature. Can you say a little bit more about this?
So there are many ways to fit this data. And a lot of the way to fit, and what has been done for a lot, was to fit this data with a power law. And the problem is that then this power law has to vary with the strain rate you use. So essentially, what people would do is that they would feed this data with a constant plus power law, but the problem is that the constant and the power and the exponent vary with the strain rate, which is not very satisfactory. You do recover a viscous.
Do you mean this?
No. If you, for example, want to feed stress versus strain rate, it looks like constant plus a power law.
But I don't know how many decades you have here, but with 4 decades of strain rate, you see a clear regime of low strain rate where it's logarithmic in the strain rate, and log rate dependence is fairly commonly seen.
Well, okay.
So
no,
but
we don't see that.
What?
We don't see that. No, but that's not.
But that shouldn't matter.
No.
Okay, well,
no.
So, what I'm talking about was certainly three-dimensional with sort of 100,000 to 500,000 particles and many orders of magnitude in strain rate.
I think there is a lot about the way you do the fits. You can fit lots of things. Okay, I'd like to stress one thing here. We have this shift here introduces two fitting parameters. So when we do this fit here of our data, it looks like there are 4 parameters, but let me explain. 2 parameters allow you to fit the values of sigma when temperature goes to 0. Now, with 2 parameters, we filled all these dependencies of all these stress versus temperature curves. All the departures of these curves from their 0 temperature limit are fitted with only 2 parameters. And I don't know of many, I've not seen any work of this type of numerical data where you can find this amount of data with 2 parameters.
Other questions or comments?
Perhaps you said it and just missed it. What's the temperature dependence of the yield stress you have? And is there anything showing up like a critical softening of the yield stress than at higher temperatures?
Well, in my language, the yield stress, there is one yield stress, which is the stress that I would get in the quasi-static limit, which is the true T equals 0, gamma dot go to 0 limit. Now, if you look here at the thermal data, if you look at the apparent yield stress, it of course varies with temperature, and it varies with something that, as far as we know, has this type of form. And okay, the log is subdominant, but what really matters is this dependency.
So how do you define the dependence?
Well, I think what you say when you say the thermal dependence of the yield stress, you have the idea that you could extrapolate this curve and find the value of the yield stress and try to look how this varies with temperature. So what I can say here is that the departure from the T equals 0 limit here is fitted by this expression. And so that's the closest thing I have from the dependency of the
But
yield
it
stress.
still contains the gamma dot, so how do I
Okay,
take the limit
that's a
gamma dot?
very important point. That's a very important point. When you do activation theory, you're not allowed to go to. You always need to make an assumption that the barrier height is large compared to the temperature. Now, if you look here at if you go to a very small strain rate, what happens at a very small strain rate is that, in fact, if you go to the low limit, you will see that at low temperature, in fact, you can go very close. What this solution tells you is that you can go very close to the saddle point. And then you go out of the situation when you can apply Kramer's expression. So, and the crossover between the two is not something that we can understand. The point is that we cannot, from these expressions, we cannot look at the T goes to 0 limit, for example, is very special, and it's not something that we can do. We can only work in the domain of the parameter, avoid the T going to 0 limit.
Okay, at the opening of this conference, David Gross said that this community, for this community, HY is equal to 0. Now, I think this is the opportunity when it is not. It may not be 0. At low temperature, if you evaluate this activation energy and use WQB or something, is it possible to have a quantum effect? I would expect, because of quantum effect, that this curvature would go horizontal or become temperature independent at low enough temperature.
No, I think the activation we are talking about here is really an activation. Okay, let me just find these barriers again. This will work. What I'm talking about applies only if you're far enough from the barrier state, because the point is that the activation will be really at work in significant anticipation of the plastic event. And so what controls this is really the vibration along the unstable direction, right? And so it's really elasticity at the scale of your particle which controls that. I think that Johnson and Samuel, they refer to some quantum effect at very low temperature. We don't, of course, have that in our simulation at all. We are purely classical.
Have you evaluated the possibility?
No.
Takeshi, I think that Anael has done this about as well as you can, given the assumptions that he's making. If you go to lower, much lower temperatures, then the barrier crossing probability is a much more difficult thing to calculate, and it requires a very complicated sort of analysis. I don't think he's done it quite right, even at this temperature range where you can do it.
We have a slight discussion on the prefactor, which I think.
I don't think. I think that's a minor technical
It's yeah.
But I think that what he's done captures the basic phenomena that he's looking at, and then the question is, okay, what are the limits of validity of that? I suspect dimensionality is very important because we've already seen that it's important just for the sizes of the events. But look, it's a perfectly respectable calculation, and I think now that they've really put it in its place of where it's relevant and what they're doing and what they're not.
So at t equals 0, you worked out the avalanche size, which is like a correlation length associated with how flips are correlated, right? Some distance over which the flips are correlated, and when is 1 over the shear rate to the 1 over dimension of space, right? Now, have you worked out anything about how that length scale depends on temperature based on the model at the end, where you even, at least in the simulation, you went above TG?
Okay, so what we, that's ongoing work to try to characterize via the same type of tools like diffusion what happens at finite temperature. The idea we have, what we seem to see, and it's very preliminary, but what we seem to see that if you are at finite temperature, say above like half of TG, you don't see any change of this correlation length, because essentially you just shift the gamma criticals, but the problem is that the strain, the instability threshold of one zone is meaningless. This is not a physical quantity, because all zones have their own thresholds. So if you just shift the thresholds, you're not changing anything to the dynamics. So you will just see the same type of dynamics. You continue to see zones will continue to receive the argument about acoustic signals. You can continue to apply it at finite temperature. In fact, you can continue to apply it provided that, okay, activation times, over activation time, you're not disturbed by this noise. But essentially, if you are at finite at small temperature, the same correlation length should be visible. And it's really when you go near TG that we start to see very significant departure. Now, there are questions about here, like at 0.2, what exactly do we see? How can we quantify this correlation length? And that's something that we're right now trying to characterize. But my guess is that in the low T limit, it starts flat.
I'm not sure how the half TG comes about, but I think in Chris Hsu's talk yesterday, where he presented this model involving STZs, there was this suggestion that if you're above 0.8 TG, that the STZ dynamics is more or less independent, which would then mean effectively that the avalanche process is become moot. I mean.
Yeah, so what we focus on is, say, the below 0.8 TG. And over this range, I don't see significant temperature thermal dependence of this length scale. And then what happens around TG, I don't know, because it's too complicated.
So you really think that if you would take half TG and you take the shear rate 0, you have a correlation?
You cannot actually cross over. It's not simple to cross over to 0 shear rate. That's one point. One point is that okay, if you have a low shear rates for any reasonable scales, yes, you should find a crossover to quasi-static dynamics. But there is not really any crossover. Okay, let me just clarify that. It's back to this problem about activity dynamics. If you are at finite temperature and you really go to the gamma dot going to zero limit, at some point you will start to activate over extremely small barriers. So from a mathematical standpoint, if your question is from the mathematical standpoint, I say no, there is no crossover.
No, my question is, at finite temperature, how does diffusion behave?
Oh.
Saying that in the zero temperature case.
Yes. I expect that temperature, I would see at low strain rates the same form of diffusion. In fact, what I showed on diffusion, the gamma dot dependence of this length scale is something that you see at very physical strain rates. It's not vanishingly small strain rates.
Could you speculate about what's happening if we go from a three-dimensional specimen to start out to a two-dimensional film to one-dimensional line? Actually, how your critical stress would change actually due to that different geometry or dimension?
Okay, so we use 2D system because I like to look at movies because I find it's interesting. But the argument, for example, about the sound is not limited to 2D, and it's likely to be similar in 3D. In the line, I don't know because it seems it's a very odd dimension. The argument about activation does not introduce any dimensionality. I mean, the fact that you have actually you are here in a very highly dimensional space, which is a configuration space, and you have local saddle node bifurcations, and that's the only thing which matters. So I think this argument should carry over in any dimension.
Could you show that picture with the blue figures back? Now, it strikes me that even especially at the lower temperatures, that I'm not sure I can distinguish that picture from the picture that Mike Falk showed of shear band formation. And I suspect that you're seeing phases of precisely the same thing. And look, remember that what Mike's theory, or our theory, is a sort of a mean field theory of the interaction between these defects, the flips, and in which basically, if they start happening in one place, there's more of them going to happen near there because of this.
Yeah. So even in AQS limit, we had these type of patterns, but we were always worried to call them shear band because actually the size of our sample, if we go back to physical scales, are 10 nanometers. Yeah. So I'm not sure we can call it a shear band.
But
well, just a quick comment to that. If it really was persistent, then it would change the scaling of the diffusion constant, right? So if this band was, stayed there forever, then you wouldn't get the scaling of the diffusion constant that he sees, right?
Well, I suspect that what happens is
Well, the thing is,
has he really tested that?
The point, Jim, one point here is that we use these Lizard-Wurtz boundary condition. And what these boundary conditions do is that they force the system to be invariant by translation. Yeah. And of course, that's very different to any experimental situation. In fact, we are working really hard to avoid any form of localization which would last. And what we see, and which is interesting, is that the system spontaneously is trying to localize, but we force it not to. So that's why we can access these steady state and steady state statistics. Now, the hope is that what we learn from that, of course, then when we try to construct a model and with the appropriate boundary condition, then you will be able to understand. We will be able to understand better what's in an experiment. But in an experiment, you have very, very particular stress inhomogeneities and boundary conditions.
Okay. Just to follow up on what Craig was saying, what I showed yesterday was that you see spatial correlations only up to the point where you get a total displacement over that region of order a lattice constant or particle diameter. That's completely consistent with the scaling with system size and gives quantitatively the prefactor for the linear scaling with system size. So at least in everything we've done on these potentials, in the steady shearing limit, they don't seem to want to persistently localize. They will localize just enough to allow enough displacement to accumulate, and then they move somewhere else. And that's at the heart of diffusion. And it does seem to be something missing from these simple potentials or these steady states that's present in the real systems. And I know that Michael Falk, in some of his work, has found that localization is very sensitive to aging. And these are somehow always in steady state and rejuvenated. So he has to quench the system and age it and create then some deeper minima, and only then does he seem to see persistent shear bends. Yeah. Yeah, but somehow here the system's sort of always forced to be homogeneous by the constant stirring.
Okay, so let's thank all the speakers again for this morning.
I just wanted to make a quick announcement that we are going to, for those of you who want to, can reconvene at 1 o'clock here. We wanted to have an extended discussion on the effect of temperature and shear rate on these kinds of simulated systems and glasses in general.